So welcome back. This is our second lecture about Bayesian networks, and now we're gonna take a look on some use case of Bayesian networks, and we'll do a little bit of modeling. So instead of trying to understand how Bayesian networks work, we'll start to look at how we can use them to model some problems. So we will start discussing 4 different types of queries that we can answer with probabilistic reasoning. And we see how those queries can give different types of answers for different problems. So we'll do a little bit of kind of using use cases and see how we can model each problem with a Bayesian network. But first, let's take a look on the software that's used to make Bayesian networks. We will not use that software in our course because we're going to use the tutorials to build our own software for making inference over Bayesian networks. But there is a software called Semlam, and this software has a nice user interface, and we can see a little bit how the inference in Bayesian networks work, and when we have independence or not. So I'm going to switch to my computer screen, and let's take a look on this software, and we'll come back to the slides. Switch it to my computer screen, and this is Semlam. That is a software developed by UCLA for Bayesian networks. So we can see in the interface of this software that we have the earthquake burglary alarm example, and it shows here to us the root variables, the internal variables, and the leaf variables. They're all binary with values yes or no. So the root variables are burglary, earthquake here on the top. Internal variables alarm, and the leaf variables call and radio. And we can take a look on the probability table. So these variables here on the top, they have prior probability tables because they are not conditional to any other variable. They have no parents, and the value for earthquake is going to be 0.1. For burglary, the prior probability is 0.02, and so these are the 2 variables that have priors. If you look at radio, we have when we have earthquake, radio can be yes with 0.9 probability. So it's very likely that if you have an earthquake, we will listen to a report. And if you don't have an earthquake, you're going to have 0.3 probability of having the report. So this report may be about an earthquake, but it's not applicable to us, maybe a different area or something like this. For the alarm, as alarm has 2 parents, it has a larger conditional probability table. If we have burglary and earthquake, we have 0.999 probability of having the alarm being activated. If we have an burglary but not earthquake, it's going to be 0.99. If we have just an earthquake, it's 0.7, and if we don't have any of them, just 0.01. And for call, we have 0.7 of receiving a call from our neighbor in the case the alarm is triggered, and it's not higher than that, maybe because the neighbor may not be at home all the time. So if it's triggered, we have 0.7 chance of receiving a call, and may have like a 0.1 chance of receiving a call in the case the alarm is not triggered because the neighbor wants to invite us to something or just talk or something like this. So these are the variables, and we can switch here to query mode. And there's something that I like about this software is the fact that we can have these monitors here. Oops. And the monitors show us the probabilities of each node. So here on the top, we have just the prior. So earthquake is 1%, burglary is 2%. For the remaining nodes that we don't have priors, we have conditional probability tables. We have to do a little bit of inference. So for radio, we have 30, around 30. For alarm, around 3. and for call around 12. And we can start observing things here to see what happens. So for instance, if I click here in yes, I am saying that I observe that earthquake is yes. So we had an earthquake. If we had an earthquake, the first thing that we can see is that radio goes up to 90%. So it was before 30 and now it's 90. So what is going on here is that this value is specified in the condition probability table that we had in this node. So basically the Bayesian network is only coming here in a specific row because it has just one parent and this parent was specified, and take the value from there. For the remaining nodes, there is a little bit of inference going on because for alarm there are two parents and just one is specified. Burglary is not. So, and we can see that alarm increased to 70 and call increased to 52, and before it was only 12%. So this is the influence coming from the top to the bottom, but it also happens that the influence comes from the bottom and influence the nodes in the top. For instance, if we receive a call from a neighbor, the probability of alarm will increase. So before it was 3, it went up to 20. The same thing gonna happen with earthquake that originally was 1%, now it's 4. Burglary was 2%, now it's 11, and also increase the radio that was around 30. Yeah, around 30%, and now is around 32. So that was a little bit surprising to me when I saw Bayesian networks for the first time. I was expecting to see the influence comes from the top to the bottom, but I was not expecting to see the influence from the bottom to the top. But remember that the direction of the edges is informing to us, if we take this causal interpretation, which variable is cause and which variable, right? But it doesn't mean that the bottom variable is being influenced by the top one, but the top one is not influenced by the bottom one, because in the end it's all probability. So these two variables are not independent. They have some thing connected to them, and when I change one, I expect it to change the other two in some way. So influence go from top bottom and also bottom to top. Actually, when you have this causal modeling, it's very common that the queries will specify values in the bottom, and we will check for changes in probabilities in the top. So for instance, if we have like a disease modeling, so on the top we will have the diseases. These diseases cause several a chain of symptoms and other things, and at the bottom there are some symptoms that we can observe or something that we can detect using a test. So we will observe nodes on the bottom of the network and make inference, and we want to understand what are the probabilities for the nodes on the top, because what we want is a diagnosis, and we need to know which of the diseases is the most likely or something like this in order to make a decision. So the influence from the top to the bottom and also from the bottom to the top. And also other things that we can do is look for independencies, right? So we learned about the D-separation algorithm. So we know that, for instance, if we change a radio, we expect it to change earthquake, change alarm, and change call, but not change burglary. So that's exactly what happens if we click here. So we change earthquake is higher, alarm is higher, call is higher, but burglary is still 2%. And we know that because here we have a common cause, and here we have a sequence, and none of those variables are observed, and so we expected this to be a chain of influence. But here, because we have this common effect structure, and this variable is not observed, so this one should not be influenced by this one. Things may change if we observe alarm, right? So if we observe alarm, earthquake and burglary, they increase because they are common cause. But if I observe radio here, it should now influence burglary too. And so it's 54. If we click, it goes to 40. So that's because we made earthquake more likely, and as they are competing, burglary decreases. So that is another thing that we can think about it, right? So we have earthquake and burglary. So we know they are independent from each other because they have this common effect structure here. So if I observe earthquake, I'm not expecting to see burglary to increase or decrease, and the same thing for burglary, it doesn't change earthquake. But if we observe alarm, okay, now the two variables become more likely. Earthquake and burglary have the value yes more likely because they are both possible explanations for the alarm being triggered. But if we know that earthquake occurred, it will be the explanation for the alarm. So the Bayesian network will decrease the probability of having a burglary because now we know that the alarm was triggered probably because we had an earthquake. So if we click here, we see that probability of burglary went down to 2.83%, very close to its original prior probability that was just 2, right? It's not exactly 2 because there is a small probability of having both burglary and earthquake at the same time triggering the alarm. So it did not come back to 2% because there is still a small chance of having a burglary. But it seems that earthquake is the cause. The same thing happens here. If we observe a burglary, the earthquake comes down to 1.01, that's almost the prior that was 1. Finally, we can observe call, for instance, and that's change everything. Going to change alarm, earthquake, burglary, and also radio. But it also makes is that it activates this structure here. So now if we observe radio, it should change burglary, right? It did not happen when we have here. So just for you to remind, you see that it doesn't change the probability of burglary, yes, but now that I have a call, observe it, and if we listen to a report on the radio yes, that's change burglary. It decreases because radio yes makes earthquake more likely, that is the probable cause for the alarm being a trigger, that is the probable cause for receiving a call from our neighbor. So it's interesting to play with Bayesian network and see how it responds to different inputs. Let's come back to the slides and take a look on some queries. Okay, so back to the slides. Let's take a look on our first type of query, and it is the simplest one. It's called a probability of evidence. So probability of evidence will give us the probability of a variable instantiation. And if you remember, when we define the variable instantiation is something like A, B, and not C. And it should be interpreted as A equal true and B equal true and C equal false. Something like this. Okay, so for instance, this example here that we have in the right, we have another toy Bayesian network in the domain that you want to diagnose if a person has lung cancer, bronchitis, or tuberculosis. And basically what we have here on the top is someone that made a visit to Asia, increasing for some reason the chance of having tuberculosis, and the person that is a smoker also increasing the chances of lung cancer and bronchitis. And we have this intermediate node here that means tuberculosis or cancer. That is a deterministic node that takes information from the nodes T and C. And on the bottom here, we have a positive X-ray associated with TB or cancer. And on the bottom here, we have dyspnea, that is the difficulty of breathing. So we can ask if a patient has a positive X-ray but no dyspnea. And in this case, we have X equal true and D equal false. So we have this variable here equal true and this variable equal false. So we call that X and D are our evidence variables, and we want to calculate P of E. So E will be the instantiation, that is X equal true and D equal false. And the big E is going to be the variables X and D. So this is one of the simplest queries that we can make it, and it will compute and return this probability to us. We could think about something a little bit more complicated. So something that goes beyond the variable instantiation. For instance, we could have a sentence like this, right? So it's not going to be only conjunctions, it will also involve disjunctions or something more complicated. But the fact is that the Bayesian network do not support those queries directly, so we have to do something different. And one technique for solving this problem is to create a new node here. It's a sort of a virtual node, and we call E for evidence, that connects to X and D, our two variables that I want to involve in this query. And we create here conditional probability table that is related with the OR operation, because we want to compute one variable or the other. So we can look in the next slide, okay, how this conditional probability table will be. In this case, E will be equal true if X or D are true. So if I have X and D, X true and D true, or X true and D false, or X false and D true. In these three cases, we have the conditional probability of E given X and D equal true, and it will be false only in the case that the two variables are false. So we call this node E an auxiliary node, and we call this technique the auxiliary node method. So we can do that to make some more elaborated queries, and this technique will work well, particularly if the number of evidence variables is small. If you increase, we have to use, if you have a very large number of evidence variables, we need to use some techniques to represent this deterministic CPT in a compact way. And there are a few of them, and we'll take a look on later on. If the probability of evidence is the simplest form of query, the most common one is the posterior margin queries. And let's first take a look at what we mean by marginal, and we will discuss what are the posterior marginals and also what are the prior marginals. So we haven't seen this before. So we have the joint probability distribution, that is a distribution over a certain number of variables n. And the marginal is a distribution over a smaller number of variables that we call m, such that m is less or equal than n. So what we do here, and we haven't seen this process before, we call it marginalization. We can take our full joint distribution and eliminate some variables by doing a summation process. So we marginalize out a few variables, and we end up with m variables. So this is the process that we call marginalization. So we can understand this marginal distribution as a sort of a projection of the joint distribution on a smaller set of variables. Okay, once we have this marginal distribution, we can compute that marginal given some evidence E. So in this case, we will have this form here, right? It's going to be a probability of those m variables that compose the marginal distribution given some evidence E, right? And we can compute this in the same process that we had before by starting with this conditional probability distribution over the all n variables, over the total number of variables that we have in the distribution, and eliminate some of the variables doing the summation process. And so there are two types of marginal distribution. One that we call the posterior marginal, and the posterior marginal is exactly this one. It is conditional to some evidence. And there is also one that we call the prior marginal, and the prior marginal is not conditional to any evidence, so it's going to be something like this. So the first one is the prior marginal, and the second one the posterior marginal. We frequently say just prior and posterior, so very common that say prior distribution or posterior distribution instead of prior marginal distribution or posterior marginal distribution. And we have a look at the SEMLAM software, and I took a screenshot here for this visit to Asia problem. And SEMLAM has the probability monitors that show us the probability of each node individually, and that is exactly the prior marginal for each variable independently. So if we take a look here, we have the variable C, and that is the prior for lung cancer. And we can compute also the posterior marginals by observing some of the variables. So here, in this case, we went here and clicked on the yes for X-ray, that's the variable X, and we clicked for no for the variable D. So we are setting the evidence that X is true and D is false. So we have a positive X-ray, but no dyspnea. And in this case, it changes the probability for node C, and that will be now the posterior probability. So before here, we have P of E with no evidence. Now here we have P of E given the evidence. Sorry, this is P of C. So this is P of C, and this is P of C given the evidence. And the evidence here is X equal true and D equal false. All right, and we see that it changed, and now it is 25% for the true value. So it comes from 5.5 to 25%. Okay, so our third type of query is slightly different from the previous ones. It's called the most probable explanation, or simply MPE. So the MPE, we need to take all the network variables, so, and also a piece of evidence, and we compute the posterior that has this form here. But instead of being interested in the probability, I'm interested in the instantiation. So the answer will be the instantiation that has the maximum probability. So we call that the most probable explanation given evidence E. So for example, we can use SEMLAM to compute that for us. If you have, for instance, a patient that has a positive X-ray and dyspnea, so we set the evidence here and here. There is a special part in the software that we go there to compute MPEs, and it gives us the instantiation with maximum probability. So in this case, the instantiation has these characteristics here, right? So the person has made, actually there's a typo here, no visit to Asia. So we can see here, visit to Asia, no. And is a smoker, has lung cancer, bronchitis, but no tuberculosis. So let me detail this a little bit more, just to be sure that you understand what I'm talking about. All right, so MPE queries are actually very simple, and just take a look at how to compute those. Let's suppose that we have the joint probability distribution that is this table here. So we have all the variables there, x1, x2, x3, till xn. xn. So these are all the network variables. And we have several rows here. Each row has a probability associated to it. So we have here one more probability of the instantiation. So this is the joint probability distribution, right? So what we're going to do is we first set the evidence. So for instance, let's say that x1 should be true. So this is our evidence. So we come here and see all the rows that x1 is false, and we take them out of the distribution. So we cancel those values. So let's suppose that it's false, false here, false here, false here, false here. We eliminate those rows. We do not consider them because they do not match our evidence. And we have another evidence, and the evidence is that x2 equal true. All right, so come here and take everything that x1 is false, x2 is false, and we eliminate those rows too. For the rows that remain, those rows match the evidence. So what we do, we consider those rows. We search here, just up here. We search here and we look for the maximum value that we can find here, right? And okay, the maximum value occurs here. We look what is the instantiation. So it's going to be true here because it must comply with the evidence. It will be true here because it's also comply with the evidence. But for the remaining values, the values will be different. So some will be true, false, no, yes, I don't know, depend on the main of each variable. So we see like false here, true here, just a few examples. False again, and true, and this is the answer, right? It is the instantiation, not the probability. It's interesting to note that the MPE cannot be obtained directly from the posterior marginals. So if we take each variable individually and we compute this probability here, the probability of the value, given the evidence that we are interested in, and we take this individually for each value and put that together, it will not result into the MPE. So we have an example here. So we set the evidence that we have positive X-ray but no dyspnea. So we have here positive X-ray but no dyspnea. And we can look at that for most of the variables, and what the SEMLAM is showing to us here is exactly what is the probability for each variable individually given this piece of evidence. So it is exactly this quantity here, the probability of the variable given the evidence. So if you look here, we see that for A, the most likely explanation is no. For T is also no. For C is no. For B is also no. And for P it's also no. But here, when you look at S, we see that yes is slightly more likely than no. So the most likely instantiation, if we take the pieces and put together, will be a no, S yes, and also no for all the remaining variables. But if we compute the MPE in a correct way, we see that the MPE is no for all variables. And it has a probability of 0.3857 or 38.57%, and if we compute this probability where smoker is yes, it's smaller than that. It's 20.03%. So we lost the most likely, the most probable explanation, and we took one that is not as likely as the MPE. And there is a fourth type of query that is very similar to MPE, and we call it MAP. It is the maximum a posteriori hypothesis. And the difference between MPE and MAP is that MPE always involves all the network variables. So if you have a network that has a set X of variables, MPE variables will be the same set. Will always include all the network variables. So that will be the network, the MPE variables, query variables. Okay, but for MAP, we will allow to have a smaller set of variables. So it's going to be a subset that we call the MAP variables, or M. So this M is a subset of X, right? The whole process is the same, right? We will set an evidence E, and we are interested in the instantiation that we call little m for the variables in M, which the probability of M given E is maximum. So it's very similar to MPE, but with a subset of variables. As I said, the variables M are called the map variables. We can understand MPE as a special case of map when the map variables include all the network variables. So we see here that M is a subset of X, but it can be equal to X. So we can grow this and make the map variables equal to the network variables. In this case, the map and MPE will be the same query. There is this distinction between MPE and map queries because MPE queries are much easier to compute. So we can come out with some algorithms specialized for MPE that are faster than the algorithms for map. The reason that MPE queries are easier than map queries is quite easy to understand, and we'll look at that with more details. So we'll have a lecture that is specific for MPE and map queries. But the idea of the idea of map queries is that it will involve a marginalization. We have to eliminate those variables here that belong to X but do not belong to M. And this process will add some computation time. So this is the difference of complexity between the two types of query. So we can use Semilan to compute map queries too. So there is one part in the software interface when we can make these map computations. And it's actually very simple. We first set the evidence in the graph, and we tell the software what are the map variables. In this case here, the map variables are A and S. And it computes and brings us the probability. In this case, the map probability is 50.74%. It's here. And the values for the instantiation of the map variables is A equal no and S equal yes. So we have here A equal no and S equal yes. So as I said, map queries are more difficult to compute than MPE. So frequently people use the MPE answer to approximate the map answer. So we compute the MPE and gives the MPE as a response for a map query, but it needs to be clear that it is not always the case that it will be the correct answer. So we say that it's an approximation. Frequently it is the same. Sometimes it's changed one or two variables, but there is no guarantee that it will be the same answer. So for instance, we can run an MPE query for the same evidence. So we still have the same evidence set here, and we run the MPE query, and we're going to see that for the map variables that are A and S, we got a slightly different result. So we got A no and S no. And before, for the map, we had A no, and S, yes. Also, the instantiation that we found is slightly less probable than what we had originally with the map query. So this is an approximation for this. Okay, so we covered the 4 types of queries, so we know what we can ask for a Bayesian network. The next thing that we're going to do is to look at the different problems and see how we can model them with Bayesian networks. But as now it's going to be a good moment for us to make a pause, and in the next video we come back and look at the problems. See you.